Hello, my name is Armand Lannard, and I'm the president of the American Chemical Society student chapter at South Dakota Mines. Every year for Engineering Week, we perform a chemistry magic show. And since this year we won't be able to do that show in person, we wanted to record the show so we could still share it with you. So, without further ado, the show.
Hello everyone, I'm Kevin Bars, a student at ACS and South Dakota School of Mines. We're going to play a little bit of a game for our first experiment. Here we have 3 cups. Who all is familiar with the cups game? Okay, well, instead of using a ball and moving it around, we're actually going to up the stakes. Here I have a vial of water, and I'm going to pour it into this cup here. So, here's where the stakes come in. If you guys guess wrong, you guys are going to get splashed. But if you guys guess right, I'm going to dump the cup of water in my head. Before we start with the thing, I'm going to put on my goggles because lab safety is important. So here we go. I may not be very good at this, but I think that will demonstrate the point nicely. Who thinks it's in this cup? Okay, 1 for 1. Who thinks it's in this cup? Okay. Nope. Well, I hope you guys are right about this. Where'd the water go, guys? Well, a fun experiment just took place. What we have in this cup is a compound known as sodium polyacrylate. Sodium polyacrylate is a type of polymer. You can think of a polymer as a bunch of a very long chain of very small paper clips. And this is what kind of the end result of it absorbing water is. And in these paper clips, each one has this tiny acrylate group, which is negatively charged and absorbs water due to a process known as hydrogen bonding. So now, who here has a baby brother or sister? Okay, a couple people out in the audience. Well, this is the same compound that is used in baby powder to absorb baby waste of sorts, but it's also used in a bunch of other industries, such as using it in potted plants to maintain water retention, and also in cables as a desiccant. So without further ado, we're going to continue with the show. Good observation skills, guys, and on to experiment number 2.
I'm Shelby Solom, and I'm a student member of the ACS student chapter, and I have a magic trick to show you guys. So I have these 4 beakers here, and I'm going to distribute this water into all 3 of them, in all 4 of them. It's the first one, and the second one, the third one, and the 4th one. And so now, I'm going to take these 4 beakers, and I'm going to pour all the contents into this beaker. So, I got the first beaker here. What do you think's going to happen? Nothing yet. Here's the second beaker. What do you think's going to happen now? Ooh, isn't that a nice color? Now the third one. What crazy thing do you think's going to happen next? Sorry, nothing this time. But this final beaker, when I take it, it turns it completely clear again. So, this is what happened in this experiment. So, I didn't quite tell you the full truth about what I did. This first beaker had a little tiny bit of sodium hydroxide in it, which is a base. And when I poured the second beaker in, which had a little bit of phenolphthalein in it, it'll lower the pH and make this able to turn pink. Because at a high enough pH, phenolphthalein will become a bright pink. This third beaker had nothing in it, and this 4th beaker had vinegar in it, which neutralized the base by bringing the pH back to around 7, which is above the range of phenolphthalein, turning it clear again. So that was my magic trick. Time for the next experiment.
Hi, my name's Charles Winkers, and I'm a member of ACS Student Chapter. Today, I'm going to show you how to make a pH indicator using this. This is red cabbage. So how we make this indicator right here, we take leaves of the red cabbage and we boil them in water for about 5 to 10 minutes, and we get this right here. So what I'm going to show you today is what happens when we add this pH indicator to various household items. So what we're going to do is we're going to do drop by drop and see what happens. And when you see the change in color, and what this indicates is what the pH of the solution is. So this is a green. So that means it's a basic solution. So let's try hand sanitizer, see what color we get. A nice pink. But let's see if we add more, if it changes the color even more. It doesn't appear so. So pink or violet means that it is slightly acidic. Next, one of my favorite drinks, Sprite, we're going to see what the pH is. Okay, so it's looking acidic, but let's see if it's mildly acidic or even more acidic than that. Color is not changed, but it is still a darker color than our hand sanitizer, so it's most likely even more acidic than hand sanitizer. So now we're going to try Windex. See what color we get. Ooh, a nice looking green. So that indicates that Windex is basic. Even darker, meaning it's even more basic than we initially thought it to be. And it looks like the color is not changing too much. So now we're going to try lemon juice and see if it's basic or acidic. You can see it's changing into a pink, which indicates that it's acidic. Let's see if it goes darker. And it's starting to turn into a pinkish red, which means it's even more acidic. And it looks like that's as much change as we're going to get with that. So now, ammonia, another household cleaner. Let's see if it's basic or acidic. It's turning green, so that would indicate that it is basic. It is a pretty cool color. And it looks like that's about it. So now we're going to try hand soap. See if it's basic or acidic. Now it's going to be kind of hard to see because it's a little murky, but it is a blue. That indicates that it is basic. I don't know if you'll be able to see that very well, but hopefully you will. And that is about as much as we're going to get with that. Our final solution is known as hydrochloric acid. And because it's an acid, it's most likely going to be acidic. Well, it is going to be acidic. So let's see what happens when we add our pH indicator to hydrochloric acid. As you can see, it is changing color with drops already and is turning into a pink. If we add more, we'll see if it's more acidic or more neutral. And is continuing to change color the more indicator we add. Now it has turned into a dark pink. That's as far as we're probably going to get with that. So what can we tell from what we've looked at? Well, first of all these cleaning supplies are basic. As we see, they're all a dark blue or a light blue or green. So this has been my experiment using red cabbage indicator to find the pH of common household items.
Hello, my name is Pascal. I'm with the South Dakota Mines chapter of ACS. And sticking with the theme we've had of different colored liquids, today I will be showing you a really cool reaction called the chemical traffic light reaction. Now, what the chemical traffic light reaction is we have our indicator here called indigo carmine. As you can see, it's this nice blue color. And what is going to happen is I'm going to add this indicator to this flask, which has a basic solution of glucose in it. And as it's added, we will watch this indigo carmine go through different oxidation states and change color. So let's do that right now. So you can see, initially upon adding it, it turns this really nice shade of green. That was the indigo carmine reacting with the oxygen in the air, putting it in its most oxidized state. And as you can see, while I was talking, it shifted over to this more red color. Now that's because the indigo carmine has begun to react with the glucose in the solution, causing it to reduce. And this red color is just one of its reduced states. So if we sit around a bit longer, you'll see that the red is starting to get a bit lighter. And if we keep waiting, it'll turn a bit more orange, and eventually it will go yellow, which is its most reduced state. And there we have our nice yellow. Now there's one more trick to this reaction. It is called the chemical traffic light, and as you know, traffic lights tend to change color a lot. We could call this reaction cyclical in a way, because if I take this flask and shake it, we will see it reacts with the remaining oxygen in the flask, and it goes back to its most oxidized state, which is its green. And if we wait around a bit longer, and ever slowly but surely back to yellow. And we can repeat this process many times up until the indigo carmine has reacted with all the oxygen and glucose in the flask. And each time, theoretically, it should go through its phases a bit faster. And that is the traffic light reaction. Thank you.
Hello, I'm Audrey Dunn with the South Dakota School of Mines American Chemical Society chapter, and today we are going to be doing a dry ice experiment. So first off, we're just going to add some soap to our big base here. Just going to add a little bit of soap, that's all it needs. You guys are looking good today. Filipova, you're looking good. Lily, looking good. Connor's enjoying his pizza. Just a little bit of soap, that's all you want. Just gonna, like I said, tiny bit. All right, so now that we have our tiny bit of soap, we're gonna go ahead and add some hot water. You're probably thinking I'm doing dishes, but we are gonna get to the dry ice, I promise. All right, so now that we have our nice soapy solution, swoosh it around, get it nice and bubbly for us. Now, we're gonna add the dry ice. So, before I drop it in there, I want you guys to tell me what you think is gonna happen. What do you think is gonna happen when I do this? Well, if you guessed carbon dioxide bubbles, you are absolutely correct. We're gonna add a little bit more. All right, get our tea kettle out of there. So carbon dioxide, as most of you know, is a large component of our atmosphere. But the atmosphere, isn't that gas? Well, yes. Dry ice is actually solid carbon dioxide. And so the process of going from a solid straight to a gas is called sublimation, and that's what these bubbles are in the process of right now. And the sublimation point of carbon dioxide is -79 degrees Celsius. When we added the dry ice to the warm water solution, it increased the temperature and started that sublimation process. Thank you for joining me for this dry ice experiment.
It's good. Just start to break it.
It's Armand, I'm back again. I'm the guy who introduced the show, and what we're going to be doing today in this experiment is something you may have done in your childhood, and it's one of my favorite experiments. We're going to be making some toothpaste for our biggest land animal, the elephant. So, to make this toothpaste, we need 3 basic things. We need hydrogen peroxide, which you can find at your local Walmart. It's used to bleach hair, it's used to bleach paper, it's used in rocket fuel, all sorts of things. It's very versatile. And then Dawn dish soap, not sponsored, but also found at your local Walmart. And then the third item, which would be potentially slightly harder to find, potassium iodide. At Walmart, a good substitute is yeast. And with these 3 ingredients and some color, we will be making our toothpaste. So what we're going to do first is we're going to add the hydrogen peroxide to our beaker. Nothing's happened. And then, as Audrey said before, we're going to add a little bit of dish soap. Swirl it together. Now you can see little bubbles forming, and if we let this sit for several days, the hydrogen peroxide would slowly decompose into water and oxygen. But we don't want to wait several days, we want to speed it up. Before we speed it up though, I need to know what colors to add. Does the audience have any suggestions? I have yellow, green, blue, and red.
Green, red.
Who said purple? You know, I'm going with purple, which is a combination of blue and red. So, let's try to make this look like toothpaste. Okay. And then, oops. Okay. Now we have colored or flavored our toothpaste. So I said it would take several days before to decompose into water and oxygen. Let's see what happens when I add some potassium iodide. Now, I want you to notice several things, besides the fact that a lot just happened at once. Do you guys see the steam rising off of this? When I put my hand over it, it's actually very warm, and you can see these bubbles forming here as well. So, what just happened? We just added what we refer to as a catalyst to the experiment, which our catalyst was potassium iodide. And what a catalyst does is essentially it provides a lower energy pathway for a reaction to take place. So whereas the hydrogen peroxide, if we let it sit for several days, would slowly turn into water and oxygen, when we added the potassium iodide in a matter of seconds, as captured by the dish soap, it rapidly turned into water and oxygen. And not only did it do that, it was what we call exothermic, meaning it releases heat, which actually, once the reaction starts and starts releasing heat, it makes the reaction happen even faster. This is the end of the elephant toothpaste experiment.
So I'm Shelby again,
I'm Connor.
and we're going to be doing the flame test. So let's light this torch first so we can get the fire going for what we're going to be doing. Strike that. All right. That looks like a good flame to me. So we're going to be taking these popsicle sticks here, and we're going to burn them in the flame. And every single element has a different color that it burns, because the electrons get excited by the heat of the fire, and they release light in different ranges. So this is lithium, and you're seeing the orange from the wood, but the lithium itself is burning this brilliant red. And the next chemical we have is calcium, and the calcium will burn kind of an orangish red. So grab one there, light that up, and there you go. It's a nice color as well. Okay.
Next,
Okay, yeah, you can talk.
the next one we have is copper sulfate, and this should be burning a nice green color.
There it is. That's the copper green. I love that color. So nice.
My favorite one out of these.
Same. My second favorite is probably either lithium or potassium, which is this one. This is potassium nitrate, and it will be a very nice purple. Look at that. Isn't that great? And the last one we've got is lead. Don't eat this.
Definitely do not want to eat this one.
And it will burn a nice bright yellow, kind of white.
Yeah, there'll be a whitish hue to it.
Yep. And those are the flame tests we have. So, yeah, let's turn the torch off. And
What's happening is the electrons are being excited by the flame. It's adding energy, and the electrons go into an excited state. And when they're in the excited state, they'll fall back down to their ground state and release light, which is the colors that you were seeing.
And the reason that the flame test is used primarily was for mining. They would take the rocks and they would grind them up and burn them, and whatever color they burned would determine what kinds of metals are present. The other reason the flame test is used is for fireworks, because as you can see, different metals burn in different colors, so they can use these to make red, green, whatever color fireworks you really want to. So that's the reason the flame test is important, and that was our experiment.
Hi guys, my name is Lily, and I am a student member of our ACS chapter here at Mines. And today, I feel like setting some things on fire. Before I do that, I'm gonna put my goggles on. And so what we have here is kerosene and ethanol. Now, just to look at them, you won't think that they're very different. They're both clear, colorless liquids. But what we're gonna see is that they burn a lot differently. We're gonna move these off to the side. And we'll pour in our kerosene and our ethanol. And then we'll just, go ahead and light them on fire. So right away what we can see is that our kerosene is burning a lot brighter orange than our ethanol is. You can even see our ethanol has kind of a blue hinge to it and a blue tint. Another thing that you can see is the smoke coming off of our kerosene. And that's because you have, it's a lot sootier flame, so it's a lot dirtier. Whereas our ethanol is burning pretty much clear, colorless almost. And so why is this important? When we're burning these types of fuels in our cars, kerosene is used in jet fuel, which is very close relative to gasoline, which we burn in our vehicles. It's a lot dirtier of a fuel to burn compared to ethanol and higher ethanol blends. And that's a big thing, especially here in South Dakota, where on the east side of the state, we have a lot of things called biorefineries. Now, these biorefineries take corn that we grow and turn it into fuels through a process of fermentation and distillation. Now, I've actually worked in one of these ethanol plants before. And you can kind of see here, like I said, there's a lot sootier, a lot darker, dirtier residue left in the bowl that was burning kerosene, whereas our ethanol bowl is pretty much, you couldn't even tell anything was burned in it. So this is why it's important to kind of start moving towards burning biofuels and higher biofuel blends in our vehicles to help keep these harmful sooty residues out of our atmosphere and to help keep our planet green. So, thank you very much.
Hello, my name is Philip.
And I'm Charles.
And we are student members of ACS here at South Dakota School of Mines and Technology, and we are here today to talk about fluorescence. Fluorescence is a phenomenon that certain molecules possess, usually dyes. And so what they'll do is they'll absorb this special wavelength of light called UV light. UV light stands for ultraviolet light, and it is a wavelength that is so high that we actually can't see with our own eyes. But these molecules will absorb it and radiate light out at a lower frequency that our eyes can detect. This is why we can see these glow. So highlighters are a good example of this because they have special dyes in them that will fluoresce. Other things that will fluoresce are driver's license. I happen to have 6 here that I found on the street. And if you look here, in the back of them, they have security features. So inside the driver's license, they actually have these special pigments that will fluoresce under UV light. And this is to prevent people from manufacturing their own IDs, which can be bad. Other things, like this club soda, contains a molecule called quinine, which also fluoresces a nice teal color. Finally, this poster here as well contains fluorescent pigments that make it nice and fun.
Well, I let Philip catch his breath because he's been talking all this time. I just wanted to remind you that these are some pretty neat features, and this is how fluorescence works.
Hello, it's Audrey again, and we are going to do a precipitation reaction. So first off, what is a precipitation reaction? Precipitation, that's rain, right? Well, kind of. So when you combine two aqueous solutions, sometimes when they're ionic, when you combine them, the ions will mix together and a solid will fall out of the solution like rain, hence the term precipitation. So when I combine these two solutions, this is lead 2 nitrate and this is potassium iodide, which you saw earlier with the elephant's toothpaste, we're going to form a precipitation reaction. And actually the name of the reaction is golden rain, precipitation rain. So take a look as we combine these two. So you can see, as I combine the two, a really bright, beautiful golden yellow precipitate formed. So that golden yellow that you're seeing is actually called lead iodide. And it forms when the positive ions and the negative ions in both the lead nitrate and the potassium iodide dissociate in solution. That means they separate into their just ionic forms. And when you combine these two ionic solutions, they get to mix and match and form new compounds. So the lead from the lead nitrate combines with the iodide from the potassium iodide, and it forms the new solid compound, lead iodide. And actually, precipitation reactions are something that's pretty common in day-to-day life. So how many of you have been to a cave? I see a lot of you that's been to a cave. All right, and even if you haven't, I've included a picture on the slide so you can see. But these common mineral formations in caves, called stalactites when they're on the ceiling and stalagmites when they're on the ground, they are actually formed through precipitation reactions. So solutions in the ground, in the rainwater that comes through, drifts down into the cave, have calcium carbonate in them. And as it drifts down, it slowly forms these mineral formations as these two solutions combine and form a precipitate. So that's a common application of this, but in the meantime, we can look at the beautiful golden rain reaction. That's it for this time.
Hello everyone, I'm back. Kevin Barr's here, member of ACS. Pascal, get over here. So, I want to see how strong this man is. So we got here like a maybe 5-liter dewar, and we also got a bunch of balloons. So what we're going to do is we're going to see how many balloons he can fit into this dewar. Okay, let's start out. 1, I'm guessing 2 max. Anyone got any bets? Okay, there's 1. Okay, let's go for 2. Okay, maybe I'm wrong. Maybe Pascal's got this. Okay. Dang, Pascal, you're really performing well under the pressure. That was a joke for all you people at home. And for those who don't understand what the joke was, Pascal is a unit of pressure, so that makes sense because strength, putting pressure on the balloons. Okay, it looks like he's going for 5. You might be able to see some steam and stuff coming off of there. Well, it's not quite steam, but we'll get into that later. Okay, well, there's the last one. Let's see. Good job, Pascal. You are truly the strongest man here. Okay. Well, he kind of cheated. We'll get into that. But what we can see here is that the balloons have actually shrunk. As you can see, as they are warming up, they're going back to be inflated. So what actually happened in this process? Well, what we have in this dewar is a substance known as liquid nitrogen. Liquid nitrogen is negative 320 degrees Fahrenheit-ish. And what happens is there's this equation known as Charles' law. And Charles' law essentially equates volume to temperature. So as you decrease the temperature, you also decrease the volume. And thus by cooling it with our negative 320-ish degree Fahrenheit liquid nitrogen, we're actually able to compress the gases inside to where the balloons essentially shrink. And usually 1 or 2 of them pop. I'm surprised that they haven't popped yet. But that goes to show you one of the effects of liquid nitrogen when it comes to gases. One other thing that we can do with liquid nitrogen is we can put flowers in them. So here we have some flowers we got for our advisor, Dr. Filipova. We got these flowers for you. Sorry we dunked half them in liquid nitrogen. Thanks for being our advisor.
Thank you so much.
She's right there. And we thought what a better way to celebrate than, stick them in some liquid nitrogen. So we can see, you might be able to hear a little bit of sound here if I be quiet. And what we're going to do is we are gonna see what happens if we break them across the table. So as you can see, it broke very similarly to glass. And this is because the organic carbons that comprise these flowers, once they get so cold, they actually go below what's called a glass transition temperature. This is a part where it goes essentially from its more amorphous, organic-y squishiness to that of glass. And as you were able to see, we were able to break it right on the table and it shattered just like glass. So what we're gonna do is we're gonna maybe test just a little something here. I'm gonna stick my hand in here. I just wanna see if it'll shatter. So let's see. Nope, we're good. So a really interesting phenomenon just happened. These flowers are about room temperature, so they're not very hot. As opposed to my body, which is a piping hot 98 degrees on average, I guess. And what happened was when I put my hand in the liquid nitrogen instantaneously boiled off of my hand, creating a lot of this gaseous nitrogen that would create a protective shield for my skin. Of course, I'm not going to stick my hand in there and keep it there because then it would start to cool down enough to where it could actually freeze and hurt me, and I'd rather keep my hand. But one other effect that we can show is racquetball. As you can see, racquetballs are very bouncy normally. And what we can do is we can put this in liquid nitrogen, and we're going to see something very similar to the flowers. I'm actually going to put on a glove because the ball is probably very cold. And we are going to pull this out, and we are going to drop it. And as you can see, much louder than before, and I did kind of trick you guys. Was that the one here? No. Still very bouncy, but you can hear it's a lot louder. And this is because all of the elasticity that was in this rubber racquetball is gone. So it's not actually compressing and bouncing when it hits the surface of the table. And if I threw this at the table hard enough, it would actually shatter. So I'm just going to try something real quick. You can see it shattered very similarly to glass. And this is because it got so cold, it went below that glass transition temperature, and it broke very similarly to glass. So now we are going to do one last experiment with the liquid nitrogen, and this will be the last experiment of the show. So we will see you once we get a couple more things prepped. Welcome back. We are finished with our preparations, and unfortunately that means this is the last experiment of our show. Thank you all so much for tuning in, but I think we're going to go out with a bang with our world famous, or at least South Dakota famous, liquid nitrogen cannon. We're briefly going to explain what's going to go on here, because we won't have much time afterwards. We are going to pour some hot water into the cannon, like so. And this hot water is a lot hotter than I am. Remember the Leidenfrost effect. I don't know how many degrees Celsius, but water is 100 degrees Celsius. And room temperature is about 25 degrees Celsius. So we're talking about a difference of 75 degrees. And what we're going to do is we're going to Lily here is going to throw this liquid nitrogen into this cannon, and that's going to cause the liquid nitrogen to rapidly boil. This will cause kind of a couple things to happen, but mainly it's going to propel all of the water that's in this tube that way across our lab benches, and that'll be it. So, safety glasses on, let's go. 3, 2, 1. Well, thank you all for tuning in, and we will hopefully see you next time.